Section 1.1 introduces some terminology about the types of signals that we're going to use throughout EE3032 and in the follow-on courses. Some of the distinctions that we need are whether a signal is continuous or discrete in time, whether it is analog or digital, and this one talks about its amplitude if we're talking about something like a voltage or a current signal. And the final term introduced in section 1.1 has to do with causal versus and related types of signals. And this has to do with when the signal occurs. So it's another aspect of what's going on with time. So mostly we're familiar with analog and continuous time signals. So this would be an example of a voltage signal versus time. It's going to have any amplitude in voltage that we want, and that can vary continuously across time. Now, if we take that signal and we put it into a computer, and this is something that's going to be important when you get into the next class, digital signal processing, we actually change the analog part first of all, we change the continuous time to discrete time. And this is called sampling. So if we sample a signal, what we do is we say we are only interested in the value of the signal at certain times, and this is a discrete time signal. It's only defined at those instants. So if you make a table of voltages that you measure off a signal, say in your lab notebook while doing an experiment, that list is a list of samples. It's discrete in time. You don't have it at all times. The other modification we might make is we go from an analog to a digital signal. And this conversion is called quantizing. And instead of having the voltage or whatever type of quantity you're measuring be able to be any continuous number, we say we're going to restrict it to certain values, and it can only be one of these distinct discrete values. So maybe we have 3, 4, 5, 6 different levels of voltage that we can represent in our system. In a computer, we could represent 6 different voltages plus 0, 7 different voltages. We could represent that, say, with a 3-bit number. So there's a discrete number of things, but now I can't represent this voltage exactly. I have to round it up a little or round it down a little. So we can think of these digital voltages as being levels to which we round off the voltage. So when you do that step, it's called quantization. So in EE3032, we're going to focus on analog continuous time signals and systems. Then what we're going to do in the next class is we're going to look at signals as they are represented inside digital computer hardware. So they are digital signals, they're going to be at discrete levels, and they're going to be sampled. That's the main concept in section 1.1. One more thing we need is we need to talk about causal and non-causal. So if I draw a graph versus time here, we normally think of a system such as an electrical circuit receiving an input that begins at a certain time. So the input to the circuit in our model that we often use is that the circuit is at rest or off or receiving, say, 0 volts of input for time, And then I turn something on, I apply some signal to the circuit, and I measure what happens. So if I look at what voltage I get out of a circuit like that, I might see starting at time 0 when I applied some voltage, I have maybe a capacitor charging up and going off and staying at some constant value here. Now, if we didn't apply any voltage before time equals 0, then we have a signal here, V of t is 0 for all the time less than 0. So that is the normal sort of system that we have, is that we have the output from the circuit is going to occur at the time equals 0, and after you apply the input, and we call that causal. If we have a signal that does not follow that, say it has values both before and after 0, we would say that is non-causal. And finally, if I have a signal that only has non-zero values before 0, then I would say that's anti-causal, kind of the opposite of causal. So these terms are going to be much more important a little later in the course when we start talking about systems such as electrical circuits, but beyond that, that modify circuits. For now, when you think of what a causal and a non-causal signal is, think of that you stimulate or give the circuit an input at time equals 0. The normal case in a realistic, realizable system is the output has to occur after you gave the system the input, and we call that causal. If something doesn't follow that, in general, it's non-causal, and if it's the opposite in time, where it only has non-zero values for negative time, then we call that anti-causal.